right, so now this fundamental theorem, whenever something's called a fundamental theorem in math, means it's really important, all right, kind of the foundational part of the concept. All right, so there's kind of two different parts of the fundamental theorem of calculus. All right, so the theorem says I have this function, all right, and it's defined this way. All right, so our function f of x is defined, it's the integral from a to x of f of x. So the basic idea is I have my starting point a, I have someplace x, and I'm finding the area under the curve f of x. And then as x moves to the right, I might get a little bit more area. Maybe it'll go negative and I'll subtract some area. But basically my function value is equal to this progressing amount of area as I move to the right with my x value. It just seems like a weird way to define a function, but it actually kind of does make sense. All right, and then the fundamental theorem says if my function's defined this way, all right, it's like f of x, if I take the derivative of that function, I just get f of x. All right, I actually made a typo here that I just realized. All right, this should be a t, because that's the t. Basically, the idea is I take this x and plug it in for that t there. All right, so if I take the derivative of this kind of weirdly defined function, then I just plug the x in there. Actually, I already said, why would you define a function this way? Kind of as your x is going to the right, you're getting more and more area under your curve. All right, so we're going to find the derivative of this function, g prime of x. Well, the fundamental theorem says I start out at a number and I go to x and I have this function. All I do is take the x and plug it into t. So the derivative of this is just 1 over x cubed plus 1. I'm just plugging that x in for t. All right, so this is kind of the simplest case. It looks just like the theorem. There's nothing else I have to do other than plug in the x. The second one, all right, now it still looks like the fundamental theorem. I start out at a 1 and I go up to something. But in this case, I have something slightly different in the top of the integrand than just an x. If I take this derivative, well, the fundamental theorem says I take this thing up here and plug it in there. So the first thing we get is sine of the square root of x. All right, so just like the same thing, I'm just taking whatever's on the top here and plugging it in to the t. But this is basically a chain rule. I have something more than just a single x in the exponent. So I'm going to multiply this by the derivative of that thing in the exponent. Derivative of x to the 1/2 is 1/2 x to the negative 1/2. So this is my final answer. It's basically a chain rule problem because I have something more complicated in the exponent up here. So I still plug that exact thing in for t, but then I have to do the chain rule and take the derivative of that thing that I plugged in. All right, so it's basically just a chain rule problem, but still using that fundamental theorem. So this problem, again, looks similar. I have this function defined using an integral. The difference here between the other ones is that I don't just have a number at the beginning of the integral, I have an x. So in order to use that fundamental theorem, I have to have a number with some x thing up there. All right, and that's when I can use the fundamental theorem. So I can't really use the fundamental theorem the way it's written right now. What I can do is manipulate it a bit. So we've used this a few times that we can kind of break these integrals up into different pieces. So what I'm going to do is instead of starting at x and going to 2x, I'm going to start at 0 and go to 2x of this exact same thing. But 0 to 2x is more than I want because I don't want to start at 0. I want to start at x. So this integral here is more than once, but now I need to subtract something. Well, what do I need to subtract? I basically need to get rid of the first part that I don't want, and that's going to be the integral from 0 to x. So I have 0 here, x, and 2x. 0 to 2x is this whole section. Right. I'm going to subtract off 0 to x, and you see the section I'm left with is x to 2x. So I basically just rewrite this using zeros, so that now I have the pattern I want with the fundamental theorem where there's a number in the bottom of the integrand. And now I can use the fundamental theorem, the integral from 0 to 2x of t cubed. Again, the 2x goes in for t, so that's going to be 2x cubed. And I have to multiply that by the derivative of the top because it's not just a single x, and that's going to be a 2. And I subtract, this next one is literally the exact fundamental theorem. I start at a number, go to x, that's going to be x cubed. And then I can just simplify a little bit. 2x cubed is going to be 8x cubed. So that turns into 16x cubed minus x cubed. All right, and that's 15x cubed. So the idea here is if you want to use this fundamental theorem, all right, it has to start with a number on the bottom. So if it doesn't, if it starts with another expression as an x, basically just break it up into two pieces, thinking about how you can start at 0 in both cases and end at your two kind of endpoints. Then use the fundamental theorem, and then you just combine like terms or whatever after that. All right, so this is the first part of the fundamental theorem, being able to take derivatives of functions defined this way with an integrand.